Welcome to this week's discussion. This is for week 4 of plane and spherical trigonometry. Our topic for this week is applied problems involving plane right triangles. The course outcome for this week is CO1, solve problems related to plane right triangles. The learning outcomes for this week is LO 1.6, which is to solve applied problems involving plane right triangles. Aside from calculating course and bearing, trigonometry can be applied in various situations involving vectors such as forces and displacement. A complex problem involving vectors can be simplified by breaking it down to its component vectors, making it easier for mathematical analysis. In this chapter, the techniques in solving applied problems involving plane right triangles are discussed. Now think about this. If a boat is crossing a river with a steady current perpendicular to the heading of the boat, is the speed of the boat faster or slower due to the drift? Will the boat reach the other side earlier or later than when it crosses a still river? Let's start our discussion with vectors. Any physical quantity like force or velocity which has both magnitude and direction is called a vector quantity. A vector quantity may be represented by a directed line segment. So as you can see, it has a arrowhead, and this is what you call a vector. It is a line segment with an arrowhead. The direction of the vector is that of the given quantity, and the length of the vector is proportional to the magnitude of the quantity. For an example, as you can see, this vector involves a displacement. So a ship is traveling 40 degrees east of north at 200 miles per hour. Its velocity is represented by the vector AB. Another example, this time involving forces. As you can see in this diagram, vector AB represents a force of 20 pounds making an angle of 35 degrees with the positive direction on the x-axis, and vector CD represents a force of 30 pounds at 150 degrees with the positive direction on the x-axis. Both vectors are drawn to the same scale. Two vectors are said to be equal if they have the same magnitude and direction. A vector has no fixed position in a plane and may be moved about in the plane provided that its magnitude and direction are not changed. Vector addition. The resultant or vector sum of a number of vectors all in the same plane is that vector in the plane which would produce the same effects as that produced by all the original vectors acting together. If two vectors A and B have the same direction, their resultant is vector R, whose magnitude is equal to the sum of the magnitudes of the two vectors and whose direction is that of the two vectors. In this example, vector alpha is equal to 75 and has a direction of east, and vector beta has a magnitude of 125 and has a direction of east. So their resultant is 75 plus 125, so it produces a resultant vector R with a magnitude of 200 and a direction of east. If two vectors have opposite directions, their resultant is a vector r whose magnitude is the difference, greater magnitude minus smaller magnitude, of the magnitudes of the two vectors and whose direction is that of the vector of greater magnitude. So for this example, vector alpha has a magnitude of 75 and a direction of east, and vector beta has a magnitude of 125 and a direction of west. Since vector beta has a larger magnitude, so that's 125 minus 75, that's equal to 50. And the direction, we follow the direction of the vector with the greater magnitude, since vector beta is the greater vector in terms of magnitude and its direction is westbound. So the resultant vector has a magnitude of 50 and a direction of west. In all other cases, the magnitude and direction of the resultant of two vectors is obtained by either of the following two methods: the parallelogram method and the triangle method. The first method is the parallelogram method. As you can see in this example, we have two vectors, alpha and beta. You simply place the tail ends of both vectors together at point O, so you connect the tails. As you can see in the second diagram, alpha and beta are connected together at the tails at point O, forming a parallelogram if you project their tail ends of both vectors. The complete parallelogram having these two vectors as adjacent sides, so it includes the directed diagonal issuing from point O, that is the resultant vector, or the vector sum of the two given vectors. The next is the triangle method. So you choose one of the two vectors and label. Sometimes it doesn't have to be two vectors, it can be more than 2, 3, 4 vectors. You can choose any one of those vectors, and you put the next vector, the tail of the next vector, on the arrow of that vector. So in this example, we chose vector beta, and then we connected vector alpha on the arrowhead of vector beta. The resultant is the line segment closing the triangle and directed from the point of origin, or O. So in this second diagram, we started with vector alpha, and then we connected vector beta with its tail connected to the arrowhead of vector alpha, and then you try to connect from the origin to the arrowhead of the last vector. In this case is vector beta, and that resultant vector is the vector sum of the two vectors. Components of a vector. The component of a vector alpha along a line L is the perpendicular projection of the vector alpha on L. It is often very useful to resolve a vector into two components along a pair of perpendicular lines. For example, we can see that we have a vector force F, a vector that represents force F. So we can try to solve for its vector components to simplify. So if this vector has an angle of 30 degrees from the positive x-axis and it forms a right triangle, so it follows that this is, with respect to the 30-degree angle, this is the opposite side and this is the adjacent side, which is equal to, adjacent would be cosine adjacent hypotenuse. So this is hypotenuse, or r, times cosine 30, and the opposite is r sine 30. Because opposite is sine of an angle is equal to the opposite over hypotenuse. You transpose hypotenuse to the numerator of the other side of the equality to get the value of the opposite side. So those are the two vector components of vector f, where the horizontal vector fh is equal to f cosine 30 and the vertical component fv is equal to f sine 30. Let's try to answer this question, this sample question, to apply what we have learned so far. A passenger boat having the speed of 12 miles per hour in still water is headed due east directly across a river whose current is 4 miles per hour due south. What is the resultant speed and course of the boat? So we can assume that the river is flowing from north to south because the river current is due south. So our river is flowing from north to south, and the boat is trying to cross that river. Due east. So the boat is heading to east. So you can expect that the boat will drift that way because the river is pushing it towards that direction. So you're supposed to find the resultant speed and the course of the boat. These are the two vectors that represent the situation of our problem. So we have the boat with heading of east and the speed of 12 miles per hour, and the river flowing at 4 miles per hour. So as you can see, the two vectors are represented in a triangle. So this is clearly an application of the triangle method. We are placing the tail of this vector to the arrowhead of the 12 miles per hour vector. You clearly have a 90-degree angle formed here. So this would be the hypotenuse, and the other sides, the legs, are 12 and 4 miles per hour. in magnitude. So since this is a right triangle, we can use the trigonometric equations to solve for the internal angles. Let's say this is internal angle x. We can just solve one internal angle besides the 90-degree angle to solve for the hypotenuse. Also, you can use the Pythagorean theorem to solve for the hypotenuse, but since our topic is about trigonometric functions, then we will try to use sine, cosine, or tangent, whichever is applicable. Since we are given, with respect to angle x, an opposite side and an adjacent side, so when choosing whether to use sine, cosine, or tangent, which of those three has an opposite side and an adjacent side? Sine is opposite side over hypotenuse. Cosine is adjacent side over hypotenuse. And tangent is opposite side over adjacent side. Therefore, we use tangent. Tangent x is equal to, what is the side opposite to angle x? That's 4. What's the side opposite or adjacent to angle x? It's 12. So in order to solve for angle x, we transpose tangent to the other side of the equality. So that's x is equal to tangent inverse of 4 over 12. You will get an answer of 18.43494 degrees. Now, since we already have an answer for angle x, we can now use that to solve for the hypotenuse. You can choose either sine or cosine. Let's try sine. Sine of angle x, which is 18.4349 degrees, is equal to opposite. What is the opposite side? 4. And the hypotenuse is unknown. So to solve for the hypotenuse, you transpose hypotenuse to the other side of the equality, and you transpose sine 18 to the denominator of the other side of the equality. So the resulting equation would be hypotenuse is equal to 4 divided by sine 18.43. And if you solve that using your calculator, you will get an answer of hypotenuse is equal to 12.649 miles per hour, or approximately 13 miles per hour. The course of the boat. The heading of the boat is due east, or 90 degrees. But since there is a drift, then the course is not the same as, since the boat is drifting towards this direction, so it's no longer 90 degrees. The actual course of the boat is 90 degrees plus 18.43. So that's 108. 90 plus 18.43 is 108.43. That's the course of the boat. So our final answer, the resultant speed of the boat is 12.649 miles per hour, or approximately 13 miles per hour, with a course of 108.43 degrees. True course. Now, follow-up question. The river current made the boat travel faster from 12 miles per hour to 12.649 miles per hour. So the river current actually made the boat travel faster. Does that mean it reaches the other side faster than when there is no river current? What do you think? Does it reach the other side earlier because the current made it run faster? Think about it for a second. Now try to answer this question on your own so that you can practice the skills that you have learned in our lesson for this week. The question is, a motorboat moves in the direction 40 degrees east of north for 3 hours at 20 miles per hour. How far north and how far east does it travel? Write down your solution and answers in your notebook. Our evaluation for this week, at the end of this week, you should be able to solve applied problems involving plane right triangles. So to access it, you just simply go to week 4 classwork posted in the online classroom for NGEZ 9, plane and spherical trigonometry. Thank you for participating in this week's lesson, and that would be the end of our coverage for CO1. So expect an upcoming exam for the first 4 weeks of coverage of lessons, and after the exam we will proceed with CO number 2. Our next topic is law of sines. Thank you, and I'll see you again next week.